We just wrapped up the soils lecture, um, all about soil texture and all the like. And now I'm excited to bring to you a lecture on biotic interactions and on disturbance. I'm going to take these things, kind of jump around a little bit, but I think you can hang with me. So biotic interactions, the way ecologists think about them. Ecologists like to think in cartoons because the world is so unimaginably complicated. It's really, really helpful to get try to get as simple as possible with how we categorize things. And so we often categorize pairwise species interactions in terms of plus minus. If we have two species, the question is what the effect each species has on the other. So we indicate that with these two minus signs or negative signs. So in this case, each species is having a negative effect on the other. So we got two species both having negative effects on each other. And these negative interactions are common in at least three situations. One is competition for limiting resources. If you have different species of plants competing for soil nitrate or soil ammonia, they're competing for those, and by taking up those resources, by each species taking up those resources, they're leaving less for their competing species. Of course, when they take that up, they're also leaving less behind for another individual of the same species, and we refer to that as intra or within species competition, intra-specific competition. These symbols refer to pairwise interactions between different species. And probably most commonly, we think of those as competition, as the most common case, as competition for limiting resources. Another case where this happens is what we refer to as intra-guild predation. Intra meaning, of course, within, and guild, just like in medieval Europe, a guild is a group of individuals, or in this case, a group of species doing the same thing. And if a bunch of predators are all feeding, they're all about the same size and they're all feeding on similar prey, well, it turns out that sometimes they eat each other as well. Predators of similar sizes can eat each other. Spiders are a classic example of this, where spiders will they're both eating flies or beetles or something. Well, they can also eat each other, and some spiders eat a lot of other spiders. And we refer to something like that as intra-guild predation, where they feed on each other. This is also common when the adults of one species feeds on the young of another, of course, because young are often easier to catch and subdue. And so it's often the case that predators will feed on the young of other similar predators. Another case, a third case that's mentioned in chapter 4 in your reading, is what's referred to as allelopathy. Plants have had millions of years to develop what we would call secondary chemical compounds. These are chemical compounds that are not directly related to growth and reproduction. And among the side effects, or in some cases the evolved adaptation, is to create poisons that poison the soil and make it harder for individuals of different species to grow. And so if two species each produce allelopathic chemicals that make it difficult for their competitors to grow, we would refer to these allelopathic interactions as negative. Now, of course, not all plants make these allelopathic compounds, but some do, and they have negative effects on their competitors. So those are the common examples of these negative pairwise interactions. We also have negative positive interactions, where one species is having a negative effect on the other, whereas the other is having a positive effect on the former. And of course, predation, all of these enemy-victim relationships are that sort of way. So in all of these cases, host pathogen or host parasite or predator prey. These think of these as enemies, pathogens and parasites as predators. Those are all, we can think of generally, those are enemies, something, and they're consuming their prey or their hosts. Now, so this species is having a negative effect on the host or the prey, and the prey or the host is having a positive effect on that which is consuming it. So we refer to these pairwise interactions as plus minus. We also have mutualisms where both species have positive effects on each other. And these actually may be the most important species interactions on the planet. Mutualisms structure vast areas of the planet's surface. When we consider the range of these things, it begins to be mind-boggling. Simple examples include plant-pollinator relationships. Most of the different kinds of food that we eat are pollinated by insects and birds and bats. And without those animal pollinators, the plants couldn't reproduce, and they wouldn't produce the fruits, the seeds, the fruits, the sweet fruits that we eat. And so each of these groups, a particular plant species and a particular pollinator species, these are each giving the other something in return for a service. So a plant is typically producing nectar, but some nectar and to a smaller extent pollen that are used by pollinators as food. And the service the pollinator is providing is they're moving gametes around, moving pollen around from plant to plant, fertilizing those plants. So the plant's providing a resource and the pollinator's providing a service. So again, most of the species in the tropics and most of the different types of foods that we eat are all animal pollinated. Mycorrhizae are at least as amazing. Mycorrhizae are fungus plant root relationships. So this is plural. Mycorrhizae is a plural term referring to these relationships between mycorrhizal fungi, and I'm going to have a whole lecture on this, so you don't need to worry too much about this, but mycorrhizal fungi and plants. And this is a resource mutualism where the mycorrhizae is providing the plant extra nutrients that it gets out of the soil and water, and in return the plant is providing the fungus sugar. And these mycorrhizal relationships provide the basis for what we think of as forests, grasslands, shrublands, and tundra. We're not going to study these much, but the coral reefs of the world are mutualisms. They are relationships between an animal, which is a coral. A coral is an animal that grows a rocky exoskeleton, and algae called zooxanthellae. And this relationship is required for the growth and survival of coral. And without this mutualism, there would be no coral reefs. And part of the problem with global warming and rising sea temperatures is that they are stressing the corals and destroying this mutualism. So let's talk about disturbances now. We'll come back to mutualisms in the next lecture, but let's talk about disturbances. As I mentioned in the lecture on climate change, we can characterize all of these things by their intensity, which is sort of their per area effect, how often they happen, or their frequency and the area over which this happens. Here we have an example from the Southern Rockies of what we sometimes call a blowdown or wind throw, where severe winds have just come through and knocked down a bunch of trees and killed them and sort of torn needles and branches off, leaving behind this pile of fallen trees. At a very small scale, we might have something like this tip-up mound. A tip-up mound is the root mat that got ripped out of the soil when a tree fell over. So a tree behind this fell over and pulled its roots up out of the soil with it, leaving behind all this exposed dirt and a hole in the ground behind it. And this creates an environment for different plants to thrive. And some plants, in some cases, especially the eastern deciduous forest where there are too many deer, sometimes the plants growing up on top of this are some of the only tree seedlings that survive. And then, of course, in this hole in the ground, we have other things that do quite well, because this area is particularly moist, and so you get areas that are kind of drier and maybe safer from deer and other herbivores, and then you get this pit of high moisture, and so you get different kinds of species growing in these different areas. And over time, this sort of slowly breaks down, and you don't maybe even notice it in the forest. You just sort of see this uneven surface to the forest, and that's the result of old tip-up mounds that have slowly broken down over time. So that here we have a small scale disturbance, and here we have a big scale disturbance. Fire, of course, is ravaging our western U.S. states right now. It's ravaging the Amazonia as well. That's sort of a different condition where it's being encouraged by the government to destroy the rainforest and open it up for cattle ranchers, and to help push out the indigenous populations that have rights to that land. But that's a different, largely political story. In our West right now, we've got a story of a natural fire regime where fire is very, very important and relatively frequent, but where it's being completely turned on its head by severity of climate change that's drying out our West, throughout the West. Mechanisms. Let's talk about how these things happen. Fire, the intensity, the extent, and the frequency of fire is determined by all of these things. It's determined by the amount of material that is there that can get burned. It's determined by how that's distributed. Is it distributed in discrete patches, or is it evenly distributed so that the fire can easily spread? What shape is the fuel in? Is all of this material that's lying, are all of these dead branches on trees and the dead organic matter on the soil surface, is that damp? Is it humid? Or is it dry as a bone, as it is throughout most of the West right now? It's determined, of course, by climate, or by weather. So if we have a dry year, or a dry month, or a dry spring, or a dry few years, that increases the likelihood of fire and the intensity of the fire and the extent of the fire. And of course, all of this fuel load, the amount of stuff that's there, and the short-term weather patterns, this is all a function of climate, right? Because climate determines patterns of vegetation growth over the long term. So the production of potential fuel, but weather, short-term patterns of weather may make an area more likely to burn in one year than another. So climate, sort of like everything that we talk about in this course, climate sort of colors all of it. But these top conditions here, the fuel and the weather, are the key determinants of fire frequency, severity, and extent. I will be sending out some required material on fire for you to listen to or read. Just a couple of terms here, crown fires and surface fires. So often, and especially in the east and in slightly more moist areas, we have surface fires may be fairly common, where a fairly mild fire will creep through the undergrowth and sort of burn up dead leaves and twigs and small branches and whatnot. The fire never really gets very hot, burns up material in the forest floor, but doesn't really damage most of the trees. In contrast, a crown fire is, as the term suggests, these are fires that get up off the forest floor and up into trees and jumps from tree to tree to tree. And those fires are kind of by definition very hot and very severe and result in a lot of tree mortality. And those are the sorts of fires that people fear out west. Crown fires are normal. Fire's normal. It's just that what we're experiencing now over the past decade or two or three have just been becoming increasingly dangerous and unusual. Fire frequency and severity that the organisms that live there simply aren't adapted to. And that's it. There we go. Stay tuned. The next one in this video series is all about mycorrhizal mutualisms and a couple other things about mutualisms.